So we're on section 2. We're going to be talking about units of measurement, define some different things involving quantities. We're going to look at SI units, which are the standard units, talk a little bit about mass and weight, and then at the end we'll do a density calculation. The last one we'll save for tomorrow, most likely, is transforming a statement of equality into a conversion factor. What are units of measurements? What we want to realize, measurements represent quantities. So if I want to find a distance or a length, that's a quantity. A measurement tells me how much distance or length I have. So that could be inches, feet, miles. All those are measurements that represent a quantity, but those two things aren't the same thing. A quantity is just something that has a magnitude or a size. So I mentioned length. Volume is another quantity, and we would use a teaspoon as a measurement to represent that. Obviously, a teaspoon and volume are not the same thing, but they're related. Just like a cup or a quart would also be ways to represent volume. The choice of unit we use depends on the quantity being measured. Like if I'm measuring a football field, I tend to use yards. That's just how we talk about football fields. I wouldn't measure it in inches because that's too small. And I probably wouldn't measure it in miles. It's probably about 1/10 of a mile for a football field, but I'm not going to measure it that way just because we tend to want to keep our measurements between like 1 and 3 digits if we can. Like if I said I'm going 7 miles, that's one distance, but if I'm going 7,000 miles, we'll say 7 meters. If I'm going 7,000 meters, at that point I'm going to want to go to the next unit up and call it 7 kilometers. It just is easier to understand that way. So I'm going to probably botch the French here, but we call the standard units SI units because of the international system of units, but it's SI and not IS because it's named after the French Le Système International des Unités. I don't know. One of you guys takes French, right? But we have 7 base units that we're going to look at. And that's, we have mass, we have length, and these are all listed on the next slide. But time, we're familiar with. Temperature. These 4 I think we're pretty familiar with. It's the next 3. Amount. You see moles all over the room. It's kind of related to what we're going to measure the amount of something in. So these 5 are the ones we're going to look at in chemistry. And then, maybe a little bit. You get into Chem 2, you might see some stuff with electric current, the flow of electricity. And then the last one would be luminous intensity. So these are my 7 base units, and we're going to define an SI unit for each of them on the next page. The thing is, I always like to show this map. This is the map of all the countries in the world that still use imperial units and not SI units. So in America, and I think, could be wrong, but I think that's Myanmar and Liberia. But those all standing strong on the imperial units, the English units refusing to go over to the SI. But in chemistry, we are going to use the SI. It is easier. And I kind of get it to some degree why we don't just switch over. There's a lot of things that it would mess up. But I was thinking we go with gallons of milk, but we go with liters of like Pepsi. It's almost more confusing because we use two different units there, but you're just used to buying a gallon of milk and a 2 liter of Pepsi and going 10 miles down the road. I think the driving thing would be the weirdest switch for me. I think I could get used to buying liters of gas, but it would be hard for me to think of how fast I'm going, I think, with kilometers per hour versus miles per hour. If you've ever been to Canada, you see it listed in kilometers, and it's a little takes a little getting used to. But here are the units that we want to use in chemistry. We have length is represented with a meter. Mass is represented with a kilogram. Time is the second. Temperature, we might be used to Celsius and Fahrenheit, but we're going to use a unit called Kelvin because it has an absolute zero. It's an absolute scale, whereas Fahrenheit and Celsius can be either positive or negative, so it makes things a little harder for us. Amount of stuff is the mole. That's why we have the mole pun everywhere in chemistry. Electric current, you may have heard amps, which is just an abbreviation for the ampere, named after a scientist. And then luminous intensity, the candela. This is probably the one we're going to use the least. It's just how much brightness is something giving off. Like the projector screen is going to have a higher luminous intensity than like the clock over there because it's brighter. So a lot of times, maybe in astronomy, you'll see that when we're talking about stars, how bright are they? Now, some of these used to have more simplistic definitions, like a meter might have been a certain length of a bar or something that you would compare your length to that to make sure you had a meter. But now it has a more scientific definition based on the speed of light. So it's how far light travels in a certain time. Bless you. Mass is the kilogram, which it's actually based on an object like this, where you have in France, in a museum, I believe, you have the piece of platinum iridium. It's an alloy, and it's just encased in a couple glass chambers, vacuum chambers, to keep it from oxidizing. And all the kilograms are supposedly based off of this. You just kind of make a copy of it, make sure that they're exactly the same mass, and then you can make a copy of that and a copy of that. So this is like the standard kilogram that's used. Oops, I don't want to go from there. So we were not there yet. So then we have the second. The second is based on a radioactive material, how fast it decays. Cesium is radioactive, cesium-133. Temperature, like I said, it's based on, it's a scaled down factor of, if we know that water has a certain place where all three forms of water can exist at the same time. You have to sort of depressurize the air, put it in a chamber, and you'll see it boiling in liquid form and in ice at the same time. But the temperature of Kelvin is based on that point. In fact, I want to show you that because it's kind of cool. The triple point of water. You can see here, this is under
If you're going back to school, before you submit your essays, run it through Grammarly to quickly check for spelling, punctuation.
This is under a a vacuum chamber. But see how you have some solid ice with some liquid, and we should start to see some bubbling. So that's actually the water boiling. So under certain temperature and pressure conditions, you can have water vapor, ice, and liquid water all coexisting.